The speed of any mechanical wave, transverse or longitudinal, depends on both an inertial property of the medium to store kinetic energy and elastic property of the medium to store potential energy. For a transverse wave, we found V equals force of tension over the linear mass density. So for force of tension here corresponds to elastic property, and linear mass density corresponds to inertial property. For a longitudinal wave, when the medium is air, we can guess that inertial property could correspond to the rho. But then what would be the elastic property? That's the question. In the straight string, potential energy is associated with the periodic stretching of the string elements as a wave passes through them. As a sound wave passes through air, potential energy is associated with the periodic compression and expansion. So this would be the compression and expansion. Of the small volume elements of the air. So the property that determines the extent to which an element of a medium changes in volume when the pressure on it changes is the bulk modulus. So which you learned in earlier physics courses, and bulk modulus is defined as negative F over A, which is the pressure over delta V over V change in volume over the initial volume, or we can write change in pressure over delta V over V. So now we can guess what's our elastic property here. Then I can say this is the bulk modulus. So in other words, I can say the V of the sound wave could be probably B over rho. Now let's consider a thin element of thickness delta X right here, that as the wave travels through the X, the element of the air, this delta X tiny element, oscillates left and right, goes back and forth, left and right, in a simple harmonic motion about its equilibrium position. Well, because when we had when we were discussing a transverse wave in a string, the string element would go up and down and oscillate parallel to the y-axis. So the string would go parallel to the y-axis. Then we wrote use the notation yxt, and in our case oscillation goes parallel to the x-axis, so similarly we could use xt. However, to avoid the confusing notation, we're going to use sxt. Then I can represent the wave function sxt equals S max cosine kx minus omega t, where S max represents the amplitude of the wave and kx minus omega t is the oscillating term. And as we know, k is the wave number, angular wave number, right? Wave number, and omega is angular frequency. As the wave moves, the air pressure also varies. Well, the question is, does it vary sinusoidally? To answer that question, let's start with the bulk modulus. So the bulk modulus equals negative change in P over delta V over V. That from here we can find that delta P equals negative bulk modulus delta V over V. Maybe this is a better expression that you're familiar to. And that equals negative B. So for the delta V, the volume, I can say A times delta S over original one is A times delta X. So the areas will cancel out. So we will end up having, we can actually write in a form of, for a tiny element, we can write B ds dx. Now ds dx, from the other end, I can take the derivative of my function s, d dx of s max cosine kx minus omega t. That equals negative k s max sine kx minus omega t. Now if I plug this one in here, I can write that delta p equals bk s max sine kx minus omega t. If we combine this bk s max together, that should be the maximum change in pressure. As this expression shows, the pressure is also changing sinusoidally. Now let's extend our discussion to evaluate the speed of sound, and let a single pulse in which the air is compressed. So let me draw that for you. So suppose that you have a tube and we have a single pulse in which the air is compressed, travels from left to right with the speed v. So let pressure of the undisturbed air be pressure, and inside the pulse be P plus delta P. Now consider a slice of air with the thickness of delta x is moving towards the pulse with the speed v. As it reaches the pulse, the leading front of the air encounters the pulse, it just slows down. The speed here becomes v plus delta v, where this delta v is a negative. As the rear face reaches the pulse, which is this one, rear face reaches the pulse, the pulse, it requires delta t time, which equals delta x over v. Now let's apply Newton's second law, which says F net equals ma. So to find the F net, let's see what are the forces acting in the system. So the force from undisturbed air would be pressure times area and then force from the pulse would be opposite direction, and it would be P plus delta P A force. So if I add them together, then let's suppose that the PA is positive. So then I would have PA minus P plus delta P A, which equals, and this is my F net, that equals negative delta P A. Now from the other end, the mass can be written as a rho times volume, where the volume in its turn equals cross-sectional area times delta x, and delta x in its turn equals V times delta t. And then acceleration can be written as delta V over delta t. Let's combine everything together. So instead of F net, I'm gonna write negative delta PA equals, instead of mass, I'm gonna write rho A V delta t, and then instead of the acceleration, I'm going to write delta V over delta t. So as you can see, the cross-sectional area will cross out, and then I would have negative delta P over delta V over V equals rho V squared. What I did, I multiplied the top expression with V and divided by V. That's how I got the bottom expression. Now let's do a little side work and see how the delta V over V, where we're talking about the speed and a change in speed, is related, whether it is related to the volume. So if I multiply this expression, the top and the bottom, by delta T times A, the top and the bottom, then I can say, I can get this equal delta V as a volume over the volume. So then I can go ahead and substitute that in my expression up here. And so it will lead us to negative delta P over delta V over V equals rho V squared. Well, we already know what this stands for. This is our Bulk modulus. So I can write the Bulk modulus equals rho V squared. From here, I can find the V equals square root of Bulk modulus over the rho. Now let's go back to the variation of the pressure and write delta P max that we found equals BKS max, can be written as V squared rho KS max. Or I can write V squared rho S max, and instead of K I can say omega over V, which will lead to an expression of rho V omega S max. So the sound also depends on temperature. I'm going to do side work in here. And the dependence of the sound wave in a temperature would be V equals 331 times 1 plus temperature in Celsius divided by 273. So depending on the temperature, the speed of sound will change. Thanks for watching and stay tuned for more to come.